So let's move on to the topic proper. Quick definition of an acid is a substance which dissociates or ionizes to produce hydrogen ions when in water. Take note, there are 3 key points here, 1, 2, 3. So without writing any of these key points, you do not have the marks for the definition of an acid. So if I can represent this with a very simple generic equation, since I get hydrogen ions, H+, I can represent my acid as HX. In the presence of water, I get H+, and X-, AQ, AQ, presence of water, this is the acid. So in water, the acid dissociates to give me H+ ions, and this is the other constituent ion that makes up the acid. So H+ of the acid gives rise to most of the properties that an acid will exhibit. So here are some examples of common acids. You notice that there are 2 categories here. One is the mineral acids and one is the organic acids. Simply put, mineral acids are mainly man-made acids, and organic acids are natural acids. So you notice that most organic acids actually have the carbon element inside, and you notice that it is a COOH, COOH, COOH. They have the COOH here. What is the COOH? It is actually the carboxylic acid group, which we will cover more in the topic of organic chemistry. So mainly we are focusing on the mineral acids here and some of the more common organic acids such as ethanoic acid and methanoic acid. You notice all of them have H, 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 and H here, H here, H here, and H here, and H here. So all the H's here can dissociate when the acid is in water to give us H+ ions. But does all the H come out? Later on we'll take a closer look at this. So let's move on to some of the simple properties of dilute acids. You would probably have tasted a lemon your whole life. You will notice the lemon tastes sour. So the sour taste from the lemon actually comes from the acid, citric acid. To be precise, citric acid. So this is the acid which gives lemon the sour taste. So the more sour the lemon, actually the more concentrated is the citric acid content in the lemon. So acids have a pH of less than 7. So the pH scale is used to measure the acidity, the extent of dissociation of an acid. Later we'll see what is what I mean by the extent of dissociation. So for now, just take note that the pH scale runs from 1 to 14, and 7 being neutral. Acids are less than 7. So pH less than 7, acid. Right? So in order for us to quickly determine if something has a pH of less than 7, we can use litmus paper. There are 2 colors for litmus paper. There's blue litmus and there's red litmus. So acids turn blue litmus paper red. The other group of compounds, the bases, they turn red litmus paper blue. So we focus more on the acids one first, blue to red. Litmus paper, blue to red. If we use universal indicator, depending on the strength of the acid, it gives us either an orangey color or a red color. Red being for strong acid, orange being for a weaker acid. Universal indicator by itself, when it's neutral, it is green in color. So acids gives red color change and bases gives a violet color change. We'll cover more on the bases later on in this topic. Now we come to some of the chemical reactions that acids undergo. So if the question were to ask you, describe a chemical property of an acid, you will need to list down the chemical reactions. So for example, one of them is the acid-metal reaction. So acids react with metals to give us the salt and hydrogen gas. So the salt, if you observe, it's essentially H being replaced by the metal. So a salt is actually an ionic compound. It is formed by replacing one or more of the hydrogen ions of the acid here, with a metallic ion. So the metallic ion here in this case is Mg2+, Sometimes it can be the ammonium ion as well, NH4 plus. So this is the salt and this is the hydrogen gas. So acid metal reaction gives us salt and hydrogen gas. We can test for this hydrogen gas. If you recall, it will extinguish a lighted splint with a pop sound. Right? So if we stick a lighted splint into a test tube containing hydrogen gas, we will have the flame going out with a pop sound. Okay? Yep, so here is the diagram. Pop sound. This one is a special case. It's more of a special case for acid metal reaction. If we put lead into hydrochloric acid, this is the reaction which will take place. It's another acid metal reaction, but now this reaction actually does not proceed to completion. So the lead block does not completely react with all the acid. Why? Because PbCl2 formed here has the state symbol S. So this state symbol S actually indicates that the layer of lead 2 chloride surrounding the lead metal is insoluble. So if I have an insoluble layer around the lead, my HCl is here. There's no way for my HCl to come into contact with more lead for the reaction to take place. So after this layer of insoluble PbCl2 is formed around the lead, the reaction will stop. Okay, so the reaction will stop. So take note, do not react lead with HCl. Acids also react with carbonates and hydrogen carbonates to give us salt water and carbon dioxide. A common carbonate is calcium carbonate. This is limestone. So limestone is used to make the Taj Mahal. So you notice that the Taj Mahal has been eroded by acid rain. The acid in rain, which makes it acid rain, is dilute sulfuric acid. So now in this case I replace it with HCl. So acid and carbonate will react to give us salt, water and carbon dioxide. Okay, so you give us salt, water and carbon dioxide. For hydrogen carbonates it's the same thing. So hydrogen carbonates with acid also gives us a salt, water and carbon dioxide. So the carbon dioxide comes from the hydrogen carbonate or the carbonate portion. And to test for carbon dioxide, we can bubble it into lime water and it gives us a white precipitate. Do you know what is this white precipitate? Make a guess. Lime water is CaOH2, calcium hydroxide. So when we bubble in carbon dioxide, the precipitate we get is actually calcium carbonate. So this is the white precipitate that is formed. Acids also react with oxides and hydroxides to give us salt and water. So this is the oxide, this is the hydroxide. Hydroxide is, you can call it a hydrated oxide of sorts. So you notice that hydroxides are always in the aqueous state. Not always, it's most of the time you see them in the aqueous state. So the hydrated oxide, it reacts with acids to give us salt and water. Salt and water. So to recall, the salt is simply an acid with the H plus ion replaced by a metallic ion. Okay, with one or more H plus ions replaced by the metallic ion. Acids can also conduct electricity due to the presence of mobile charge carriers, which are ions. So from the first definition of an acid is a substance which dissociates in water. Dissociates in water to give you H plus ions. So notice that when HCl dissociates, you have H plus and Cl minus. So if I have a solution here with H plus and Cl minus inside, and I were to stick in 2 electrodes here, one with a positive terminal, one with a negative terminal, my Cl minus will migrate to the positive terminal, my H plus will migrate to the negative terminal, and this migration actually contributes to the flow of current. So in a sense, I'm saying that dilute acids can conduct electricity. Why? Because they have mobile charge carriers. How did these charge carriers come about? It came from the dissociation of the acid into the ions. So if I combine H2SO4 and HCl, I will be able to make a deduction that this is actually a better conductor than HCl. H2SO4 is a better conductor than HCl. Why? Because for every unit of H2SO4, I have 2 plus 1 unit of ions versus 1 plus 1 unit of ions. So I have 2 units of ions here, I have 3 units of ions here. So because I have more mobile charge carriers, I can make a deduction that H2SO4 is a better conductor of electricity. Okay, now we move on to this very important area on water being required for the properties of an acid. So if you recall the definition from earlier, the acid must dissociate to give us H plus ions in water. So H plus ions only exist in the presence of water. Without water, you have no H plus ions. No H plus ions, you cannot have an acid. And because the acidic properties of an acid comes about from the presence of the H plus ions, so if I have HCl reacting by itself, there will be no reaction. It's only when HCl dissociates into H plus and Cl minus and the H plus undergoing the reaction here, then I can observe the acidic properties of HCl. So without water, no H plus, no acidic properties. Right? So if you have seen this before, this is an example of effervescence tablet. The tablet by itself remains relatively inert, but once you pop it into a glass of water, you notice fizzing happening. So this fizzing is actually a reaction between an acid and a carbonate. What acid is being reacted? It is actually citric acid. So in the tablet, there is citric acid in the crystalline form. So in the crystalline form, there is no water present. It is just a citric acid molecule, no water. But when you put it into the water, into this cup of water, water is present. Citric acid dissociates to give you H plus ions, and these H plus ions react with the carbonate in the tablet, giving rise to the fizzing. So this fizzing actually helps to break the tablet into smaller pieces and dissolve the tablet well in this cup before you drink it, of course. So, to recap, an acid does not behave as an acid unless water is present. We need to have AQ for the H plus ions to form through dissociation of the acid molecule. No H plus, no acid. So how do we confirm this? It's actually very simple. So if you recall the earlier properties of the acid, these are the tests based on the properties of the acid. If I dissolve HCl in water, I will have the H plus ions. If I dissolve HCl in methyl benzene, this is an organic solvent, means no water, so I have no H plus ions. The HCl in water will be able to turn my blue litmus paper red. This one remains blue. Why? Because there's no H plus. It can conduct electricity. Why? Because my HCl is now dissociated into H plus and Cl minus. Over here it remains as HCl molecules, no dissociation, no mobile charge carriers, so cannot conduct electricity. I add magnesium ribbon. I have my HCl reacting with Mg to give me my salt plus hydrogen gas. So I get effervescence and I have hydrogen gas. No visible reaction because there's no H plus again. This is my base. Adding a base can react with HCl, so this is acid-base reaction. I can get a blue solution of Cu2 plus ions. Over here, no visible reaction as well. Adding carbonate, I have an acid-carbonate reaction, so this is an acid-carbonate reaction. And I have my CaCl2 plus H2O plus CO2. So I observe effervescence, and I observe the evolution of carbon dioxide. Why? Because H plus is present. No H plus, no visible reaction. Why? So why do I keep harping on the point that there's no H plus? There's no water, there wouldn't be any H plus for any reaction to take place. This is because acids, in the absence of water, is actually a small covalent molecule. So let's recall how do we draw HCl. If I were to draw the dot and cross diagram for HCl, it will look something like this. Okay, so HCl, single bond. HNO3 is a bit more complicated. It's something like this. And H2SO4 is a bit more complicated. It is something like this. So notice that in all these three molecules here, they are all covalent molecules, and they all have covalent bonds. Covalent bonds, covalent bonds. And the covalent bonds actually bind the H to the oxygen atom here. Okay, or it binds it to the chlorine atom here. So the H cannot be released. So it is just a simple molecule by itself. But when you add in water, the water molecule can actually remove the H from the acid molecule. So it gives us the H plus ion, which then can allow us to have all the observations for the different reactions of an acid. So actually, to be more precise, if you observe this equation here, the H plus ion is in fact something like this. It is formed between the reaction of water with the acid. It gives us H3O plus Cl minus. So this is called the hydrozonium ion. But for O level, we simplify this into the H plus ion. So H plus is sufficient for O levels. H plus, and H plus. So this process by which the acid breaks out the H plus is known as ionization or dissociation. So when I have an organic solvent, nothing happens. I simply dissolve the HCl and it forms a liquid HCl. So how do the organic molecules dissolve HCl? Is by means of van der Waals forces, if you recall. So the weak van der Waals forces, they bind the HCl molecules and then they disperse them in solution, allows the HCl gas to dissolve. But when it dissolves, there's no dissociation happening. This doesn't take place. This doesn't take place. So there's no H plus. So no H plus, no acidic properties. So now let's move on to checkpoint 1. Pause the video now to attempt this checkpoint. Continue with the video once you are done. So what are the 3 properties of an acid? Earlier we recalled we have a couple of them. Sour taste, pH less than 7. We have the reaction with metals to give us salt and hydrogen gas. We have the acid carbonate reaction to give you salt, water, and carbon dioxide. Acid metal oxide reaction give you salt and water. The ability to conduct electricity. So here is it. You have the main property, sour, less than 7. It reacts with metal to give you salt and hydrogen gas. Carbonates or hydrogen carbonates give you salt, water, and carbon dioxide. With oxides and hydroxides give you salt and water. And it can conduct electricity due to the presence of mobile ions. So what equations can we write to show the reaction of dilute hydrochloric acid with carbonates and lithium? So this is a acid carbonate reaction. What do we get? We have 3 things. We have the salt, we have water, and we have carbon dioxide. With acid metal, we have salt and hydrogen gas. So first one, Na2CO3 plus HCl, NaCl plus H2O plus CO2. How do we know what is the salt? It is actually a very simple trick. Just take the first one and the second one and we do a swap. Because if you recall, the salt is an acid with the H plus replaced by a metal ion. So there's only one acid here, which is HCl, and there is only one other metal ion here, which is Na. So you can only replace the H of HCl with Na from Na2CO3. That's why we have NaCl, sodium chloride here. The rest of it is the generic equation, water and carbon dioxide. So lithium with water, lithium with acid. What do we get? Same things as usual. The salt, LiCl, the H of HCl is replaced with the metal. So the only metal here is Li. So we put in Li, LiCl, and we have H2. This is from the generic equation. So acid plus metal gives us salt and hydrogen gas. So quick recap. How do we test for this? It extinguishes a lighted splint with pop sound. Lighted splint and extinguish with pop sound. What about CO2? It forms a white precipitate in, yes, lime water, correct. And recall what's lime water? Lime water is CaOH2, calcium hydroxide. Now let's write three equations to show the reaction between dilute sulfuric acid with potassium carbonate, magnesium and sodium oxide. So the first one is an acid carbonate reaction. We will have salt, water and carbon dioxide. Acid metal, we have salt and hydrogen gas, and acid sodium oxide, we have salt plus water. So now we have this, we will be able to write this out. K2CO3 plus H2SO4 gives us salt, water and carbon dioxide. Acid metal, salt and hydrogen gas, and acid oxide gives us salt and water. Take note, SO4 has a charge of SO4 2 minus charge, H plus. That's why we have two H's here. K is in group 1. Group 1 means that it will lose a single valence electron to form K plus. So to balance 2 minus and plus, we need 2 of the K's. Mg is from group 2, so it loses 2 electrons to give Mg2 plus. So we just need 1 Mg2 plus to balance the SO4 2 minus over here. Na, as usual, is the same. It is from group 1, so we get Na plus E minus. So in order for sodium sulfate to be charged neutral, we need 2 Na plus to balance away the 2 minus from the sulfate ion. So now let's go on to the basicity of an acid. There are 3 main basicities here, which we will cover for today. One is the monobasic acid. If you see, it's quite obvious. Mono means 1. So each acid molecule only gives 1 H plus if it is dissociated. Dibasic acid or diprotic acid. Protic is basically the word for proton, because H plus essentially is only one single proton. Because hydrogen is 1 proton and 1 electron. When it loses the 1 electron, it's left with 1 proton and it gives the H plus. So this is a monoprotic acid or monobasic acid. This is a dibasic acid or diprotic acid. So you notice each molecule, when fully dissociated, can give us 2 H plus. So this is supposed to be H. This is out. Not here. This is supposed to be over here. Okay, so tribasic acids or triprotic acids, H3PO4, H3PO3, when they dissociate, they will give us 3 H plus ions each. So this refers to the maximum number. Notice this is the maximum number of H plus ions that can be replaced by a metal. So it doesn't need to replace all 3 at the same time, but this is the maximum number that can be replaced by a metal during a acid metal or acid salt or acid oxide reaction, or one of the other reactions which covered earlier in this topic. Okay, so for example, if I were to write a simple one, H2SO4 plus, let's say, magnesium, we'll write MgSO4 plus H2, but it can also replace just one H. So for example, if we have H2SO4 with sodium, we could get NaHSO4 plus H2. Okay, so this is possible as well. Balance the equation with a half here. So this is the first step of the reaction. The second step will be the HSO4 minus, Na is plus, so this is HSO4 minus. it can be the HSO4 minus reacting with another Na to give us Na2SO4. So it's a two-step reaction, which we always write as a single step, such as this. So let's quickly do checkpoint 2. We have 3 acids here, 1 monobasic, 1 dibasic, 1 tribasic. So write down the dissociation equations to represent these 3 types of acids. So monobasic one, you could think of HCl, we have 1H plus, dibasic one, probably H2SO4, and we have 2H plus, 2, 2, 1, 1, and the tribasic one we have phosphoric acid, H3PO4, this is phosphoric acid, and when it dissociates fully, we have 3H plus ions. Now, let's move on to an area which is often confused by many people, the strength of an acid versus the concentration of an acid. So, take note, these two terms are not the same. The strength refers to how much it is dissociated. So for example, HCl I would say is a strong acid because it is fully dissociated. So if I have 1 mole of HCl, at the end of the day I will have 1 mole of H plus and 1 mole of Cl minus. So let's ignore this part first because this is the more important part. If I have 1 mole HCl, I would get 1 mole of H plus in water. Because why? HCl is fully dissociated. The HCl bond breaks to give me H plus and Cl minus. So weak acid is one which is partially dissociated. It means it is not fully dissociated or not fully ionized in water. For example, I have ethanoic acid over here. You notice that the arrow here is a reversible arrow. This is a reversible arrow. So it shows that the reaction, this reaction step is not complete, and only some of the ethanoic acid molecules actually dissociate to give me H plus and the ethanoate anion. So because it is not a full 100% dissociation, if I have 1 mole of this, I will have much less than 1 mole of H plus, much less. So this means that this acid is a weak acid versus a strong acid which is fully dissociated. So this is a very simple pictorial representation. I have all my HCl fully dissociated, but I only have 1 ethanoic acid molecule dissociated. So this is a weak acid, partial dissociation, and this is a complete dissociation for a strong acid. So as a result of this, what happens? It means that strong acids react more vigorously than weak acids in the same reaction. So if I have magnesium ribbon here, let's say this is magnesium ribbon. So Mg plus HCl, I have a lot more H plus compared to ethanoic acid. So because I have a lot more H plus, the reaction proceeds more vigorously, and I get more H2 gas being evolved. And as a result, when I do my Leydig spleen test, there's a much louder pop sound. Pop versus pop. This is a loud pop versus a small tweeny pop. So now let's move on to concentration of an acid. So versus strength, what is the difference? Concentration is simply the amount of acid per unit volume. Con is the amount of acid per unit volume. So I can have a concentrated weak acid and I can have a dilute strong acid. So for example, if I have HCl, this is a strong acid. If let's say I only have 0.1 mole in 1 dm cube of solution, my concentration would be 0.1 moles per dm cube. And if I have my ethanoic acid here over here, and I have say 1 mole of ethanoic acid, and I have the same volume of water, I get 1 mole per dm cube of ethanoic acid. So this is a higher concentration of weak acid, but I do not change the strength of the acid. So this is the strength. The strength remains unchanged. The strength is only dependent on the acid itself. The strength is dependent on the acid itself. The concentration is dependent on the initial amount or mass you add into the water. So take note, make sure you are very clear on this. The strength is only dependent on the acid itself. You cannot change the strength of an acid by using more or less of the acid. It is dependent on the acid. HCl is forever a strong acid, ethanoic acid is forever a weak acid, but I can have a concentrated solution of a weak acid and a dilute solution of a strong acid. So this is a quick table which summarizes this. This is 10 moles per dm cube. Let's say I have a con solution of a strong acid. This is a dilute solution of a strong acid still. This is a con solution of a weak acid, and this is a dilute solution of a weak acid. The con does not affect the strength of the acid, right? The con does not affect the strength of the acid. Very important point, take note of this. So over here you'll see some examples of acids in everyday life. The first one is the effervescence tablet, which we have the citric acid. So this is actually a weak acid. You have dilute sulfuric acid in your car batteries. This is a very strong acid. Over here we have a bomb. So the bomb, there can be acids in the bomb. Nitric acid is one such acid in bombs. So nitric acid is a strong acid. And soaps, some soaps contain acids. Why? Because your skin is slightly acidic, about pH 5.5 around there. So to balance the pH of your skin, the soap sometimes contains a little bit of weak acid, such that when you wash your skin, the soap is at the same pH as the skin and it wouldn't damage or dry the skin. So these are useful uses of acids. But are there not useful uses of acids, or harm which acids can cause? Yes, of course. So acids in the environment. For example, take a look at this. This is a power station which burns coal. Coal contains loads of sulfur, and when you have loads of sulfur burning in oxygen, you get sulfur dioxide, and sulfur dioxide can dissolve in water in the rain to give us acid rain. Similarly for here, this is the exhaust pipe of a car. You have loads of stuff coming out. For example, you have carbon dioxide. Carbon dioxide, you have nitrogen dioxide. So these two oxides can dissolve in water to give us acids as well. So the first one gives us carbonic acid, and the second one gives us nitrous acid or nitric acid. So all these are acids which are bad for the environment. So we will touch a little bit more on acid rain. The sulfur dioxide which comes from burning of coal can dissolve in water first to give us sulfurous acid. Take note, this is SO3. SO3, not SO4. So how do you know it's 3? Very easy. 1, 2, 3. There are 2 here and there is 1 here. So 3, sulfurous acid. So in the presence of oxygen in the air, your sulfur dioxide here dissolves in oxygen. Can be further oxidized to give us SO3. So this is sulfur trioxide. And sulfur trioxide can dissolve in water to give us dilute sulfuric acid. This H2SO3 formed here can also be further oxidized by oxygen in air to give us sulfuric acid. So all this contributes to acid rain. And this is no good. Why? Because it destroys your structures, it damages crops, it kills fishes. Basically, it's no good, no. The Taj Mahal has been partially dissolved by acid rain. Large tracts of land have been made barren and unsuitable for farming because of acid rain. Lakes have been polluted and the fish have been killed because of changes to pH, because of acid rain. So how do we reduce acid rain? We must reduce the sulfur dioxide. How do we reduce sulfur dioxide? We must stop burning of coal. How do we stop burning of coal? We can switch to alternative fuels, or we use less electricity. So do your part and save the environment. Nitrogen dioxide formed through industrial processes can also dissolve in water to form a mixture of nitrous oxide and nitric acid. So NO2 is mainly formed in car engines. It's mainly formed in car engines because the very high temperature in the car engines can allow for the very strong N triple bond to break and react with oxygen to give you NO2. So NO2 is released into the environment. It dissolves in water, gives us nitrous acid and nitric acid. So these two acids also contribute to acid rain. And even in the absence of these pollutant gases, rainwater will be slightly acidic. Why? Because air contains carbon dioxide. 0.03% of air is carbon dioxide. And carbon dioxide is soluble in water. So even without any pollutants, CO2 can dissolve in water to give you carbonic acid. This is a weak acid. So rainwater is slightly acidic. Okay, so if you have the chance to get some litmus paper, you could probably get it from the lab, or you can buy them from the Guardian or Watson's pharmacy. You can collect some rainwater in a cup next time it rains and dip in the litmus paper to see the color change from blue to red, indicating that rainwater is actually acidic. Yep, so this are some pictures showing the detrimental effects of rainwater. No good. Kill fishes, destroy plants, destroy statues. Basically, no good. No good.